Good afternoon, Advanced Kentucky AP Chemistry students and teachers. And I'm glad you're here for our content review session in thermochemistry and calorimetry. Our speaker today is John Gelder, a misspelled Oklahoma State University.
That's
near
okay.
Oklahoma, just north of Texas. John was an AP Chemistry chief reader and a personal friend and my roommate for a while at the reading.
Yeah.
So welcome to John. It's good to see him from Oklahoma, Stillwater. I'm Lou Akampora, and I'm assisted by my staff, my colleagues, they're not my staff, and many of you might know those names. We will have quite a few participants here, so please do mute your microphones and turn off your video, but feel free to use the chat box. We'll be soliciting some input from you, including polls, which are anonymous, so don't be afraid, and some chatting. This session will be archived and available at kyap2020.com, along with some notes that John has prepared for us on thermochemistry and calorimetry, which will be an important part of the AP Chemistry exam in about 3 weeks. So once again, here is John Gelder, and that is, oh, I learned how to spell Oklahoma by now. Hey, John, you may take it away.
All right, so I'm going to share my screen and somewhere, OneNote, and share, okay. All right, well, thank you, Lou, or Mr. Akampora, thank you very much for that introduction. And I'm here today, and we're gonna do a bunch of thermochemistry and some stoichiometry. I think Lisa McGaw was doing stoichiometry last week. And the interesting thing about thermochemistry is that we do a lot of other chemistry with calorimetry or thermochemistry. And so I wanted to sort of remind everybody that if you were able to get a copy of the PowerPoint, the PDF that I had shared with Mr. Akampora, you might need a calculator, periodic table, and an equation page from the 2020 AP Chemistry exam. And so I think the PowerPoint that I gave to Mr. Akampora is the same one that I will be using, and I'll be writing in it today. So, anyway, let's get started. What we're going to do to sort of get started is to have some poll questions to sort of get some idea of your intuition about heat, mass, and change in temperature. And just as a quick reminder about heat and its units are joules or kilojoules, and mass has units of grams, and temperature is measured in units of degrees Celsius. And so let's go ahead and we will look at sort of the first question, which is going to be a poll question. It will be choice A or choice B. And so I'm going to sort of move that poll question a little bit. Lou, if you tell me if it goes off the screen, but I hope everybody can see two beakers.
They can move their own poll question, John. They won't see yours.
All right. So you can see two beakers. One on the left has a volume of 25 milliliters, the one on the right, a volume of 50 milliliters. And as it says here, both of the initial temperatures of those two samples of water is the same. And we're going to add the same amount of heat to both beakers using a Bunsen burner. And what I would like to know, does the beaker on the right, your right, or the beaker on your left have the higher final temperature? So for A would be the beaker on the right, and B would be the beaker on the left. And so which will have that higher final temperature, the beaker on the left or the beaker on the right?
Is A right or is A left here?
I think we were going to say A was right and B was left. Is that what we said?
Right on your screen, an A and a B.
Yeah. A is the beaker on the right. B is the beaker on the left.
Just with your pen.
Oh, I can, okay, here, yeah, there's the beaker on the right. That would be A. And there's beaker on the left is B. Well, actually, that's sort of a, let's not put B there. Let's put B right here. Which is going to have that higher final temperature.
Why would you not read from left to right, A and B? How confusing.
There's A. So 80%, 20%. And so, yes, I agree with the students with 80% that it's going to be the beaker on the left is going to have the higher final temperature. And so let's go to this. And so I'm going to say left. And then I've got another question that it's not a poll question, but what I'd like to do for us, have us consider in this experiment, Q, the amount of heat that was added to each of the beakers was the same. What's the relationship between mass and change in temperature? Is it a direct relationship or an inverse relationship? That's what we want to think about. So in this particular case, we saw that the higher change in temperature was going to be the beaker that contained the smaller amount of water. And so that's an inverse relationship. And so we can talk about that relationship as the change in temperature is proportional to 1 over the mass. Now, I know I gave you volumes of water in these two cases, but I think we all remember that the density of water is 1 gram per milliliter. So if we can do that direct connection between mass and water. So the delta T, the change in temperature, is inversely proportional to the mass. So let's go to the next slide because I have now the next question. In this particular case, again, we have 2 samples of water with different amounts. And in this particular case, again, they have the same initial temperature. If the final temperature of the water in both beakers is identical, is the greater amount of heat added to the beaker on the right, A, or the beaker on the left, B? So in this case, we're going to have the same final temperatures, and we want to know in which sample are we going to have to add more heat to get that same final temperature in this particular case. And I'm seeing that everybody is going for beaker A, the beaker on the right. And I totally agree with you on that one. So let's go to the next slide, because now what I want to do is I want to, again, think about that relationship. Here, we're going to have the same delta T. The delta T is constant. What's the relationship between heat and mass? And in this particular case, Q, which is our symbol for heat, is directly proportional to mass. So to have the same final temperature, the more mass we have, the more heat we're going to have to add. Okay, so let's go to our next slide, because this next slide is sort of a summary of the 2 experiments that we've done. In the first experiment, we looked at constant heat, Q, and we saw that delta T was proportional to 1 over mass. And we saw in the second experiment at constant delta T that Q was directly proportional to mass. So we've done two experiments, one at constant heat, the other one at constant T, and we looked at the relationships between the other two variables because we're interested in heat, mass, and change in temperature. So can you imagine a third experiment that we've done? We've done one experiment with constant heat, one experiment with constant delta T. What would be a third experiment? What would we hold constant and investigate the other two variables? So I'm hoping that you're thinking the same thing I'm thinking. Well, let's see, if we're investigating heat, mass, and change in temperature, then we would want to keep the mass of the two beakers constant and ask, in this case, we're going to add twice the heat is added to the beaker on the right. So that's beaker A. Then compared to the beaker on the left, beaker B, does the beaker on the right or the left have the highest final temperature? So we're going to add twice the heat to beaker A, and we want to know who's going to have the final temperature, A or B. If we add twice the heat when we have the same amount of water in both of those beakers. And so it looks like 100% of you, we've got one going for B, but the majority of you are agreeing with me that beaker A, when we have the same amount of water, the more heat that we're going to add, the higher the delta T. And so what we can do is think about this relationship. Here we've got mass constant. So when mass is constant, the delta T is directly proportional to, whoops, I didn't want to do that. I don't want to do that with, I want to put Q is directly proportional to delta T when mass is constant. So, so now, and I'm going to jump back just a couple of slides to this slide, and we've got experiment number 3, and we saw that Q was proportional to delta T at constant mass. And so what we can do with just doing those 3 experiments, we can start seeing, oh, check it out. Q is directly proportional to mass, Q is directly proportional to delta T, and delta T is inversely proportional to mass. So we could write a proportionality with these 3 variables, that Q is proportional to mass times delta T. And that simple proportionality summarizes those 3 experiments very nicely. We can see Q is directly proportional to mass and delta T, and mass and delta T are inversely proportional. And so to make a proportionality an equality, what we would do is we would add a constant. And so that constant is called C, called the specific heat. And the specific heat has units, if we sort of rearrange this equation, has units of Q, heat, over mass times delta T. So it has units of joules per gram degree Celsius. And a specific heat, it pretty much tells us how much heat is required to change the temperature of 1 gram of substance by 1 degree Celsius. So we could think about a substance like water, which has actually a very large specific heat, 4.184 joules per gram degree Celsius. So it takes 4.184 joules to change the temperature of 1 gram of water by 1 degree Celsius. Whereas a metal like iron or aluminum or copper, those metals have specific heats that are less than 1. So it doesn't take very much heat, very many joules to raise 1 gram of a metal by 1 degree Celsius. And so this relationship, and I'm going to jump up ahead here to the slide that has the relationship that I'm looking for. Here's that relationship that we just sort of came up with. But what's this word say about that relationship? It says danger, Will Robinson. We got to watch out for this, because this relationship, and it is an equation on the equation page for the AP exam, is very useful in calculating the magnitude of the heat released or absorbed, but it doesn't tell us anything about the sign of Q. And so one of the things we have to sort of think about this relationship is that this is an identity relationship. We don't want to actually use this relationship to solve for any of those quantities. We actually want to use it as an identity relationship. And what I mean by that is, let's go here to think about where are situations in AP Chemistry where we're interested in using mass, specific heat, and delta T. And so here's a series of experiments that we do in actually first year chemistry and in AP Chemistry. So in a pre-AP Chemistry course, you might do some of these experiments. We might mix hot and cold water. We might add a piece of hot metal to water at room temperature. We might add an ionic solid to water. And some of you might have done an experiment like that where you investigated dissolution of ionic solids in water. We might mix a strong acid and a strong base, or we might mix a strong acid with a reactive metal, which actually is one of the experiments one of the problems that we'll look at in just a moment. So those are the kinds of experiments that we would be doing in pre-AP or AP Chemistry to sort of investigate heat transfer and to investigate that relationship between mass, specific heat, and delta T. But the problem with that equation, Q equals mass times specific heat times delta T, is it doesn't give us the sign. And so what we need to do is think about the first law of chemical thermodynamics. And when we think about that first law, remember the first law can be stated in many different forms, but it essentially says that we can't create or lose energy. Energy is transferred within its different forms. And the way we sort of express that first law relationship is to write mathematical relationships. For example, when we mix hot and cold water, we know the heat lost by the hot water is going to be gained by the cold water. If a piece of hot metal is added to cold water, we know the hot metal is going to lose heat to the cold water. And whatever amount of heat the piece of metal loses, we assume the hot water or the cold water gains. And in an ionic solid, when we think about the dissolution of the ionic solid, which can be exothermic or endothermic, we think about whatever heat is lost or gained by that dissolution process is lost or gained by the solution. And again, we can do that same thing with a neutralization reaction between a strong acid and a strong base, or if we take a strong acid with a reactive metal. So when we think about this Q equals mass times specific heat times delta T, and the statement that we can calculate the magnitude of the heat release, but not the sign of Q, let's think about an exothermic reaction in which some reaction occurs in water in the solution. And we know that if a reaction is exothermic, that the final temperature is going to be higher than the initial temperature. And remember, delta T is always T final minus T initial. So the delta T term in this relationship is positive. Specific heat is always a positive quantity, and mass is always a positive quantity. So if we look at that relationship with all three of the terms positive, our heat comes out positive. But we know that for exothermic reactions, that we think of heat as negative. We think of delta H as negative. And so we can see this issue that we have to be careful with this relationship, that we lose a sign if we just look at Q equals mass times specific heat times delta T and try to solve for heat using that relationship. But if we use the first law statement where we have some reaction, Q of a reaction is equal to minus Q of the solution, and that's equal to minus the mass of the solution times the specific heat of the solution times the delta T of the solution. All of these quantities are positive, but theirs are negative so that we don't lose that negative sign. And over the years that I and others who have graded the AP exam, we see that this thermochemistry kind of question where we're using Q equals mass times specific heat times delta T usually has 2 points associated with that question. One is for the magnitude of the heat transferred, and the other point is for the sign. And it's the sign that so many students lose a point on the AP exam. And so as an example of that case, let's look at a question from a 2013 AP Chemistry exam. And so in this question, we might take note of a lot of information. And this question is very similar to the kinds of questions that we're seeing these days, in that we've got a chemical reaction, we've got a bunch of information, and then we've got a table of data. And so when we look at this particular problem, we see that the equation, the chemical reaction, magnesium oxide reacting with hydrogen ion to produce magnesium ion and water. And in this, the student has a task of determining the enthalpy change of this reaction. And this is kind of a cool reaction because when we do it in a solution, in this case of HCl, that's a solution. So we're doing the reaction in water. And we know that if we can measure the delta T, the change in temperature of a solution, and we know the specific heat of the solution, and we know the mass of the solution, we can calculate Q, which is our goal, part of our goal in getting the enthalpy change for this reaction. So we've got this reaction. We've got apparently 4 trials because the student, it says here, a student uses a polystyrene cup calorimeter to perform 4 trials. Data for each trial are shown in the table below. So we've got 4 data points, 4 trials, where we've got a volume of hydrochloric acid, a mass of magnesium oxide added, an initial temperature for each of those 4 systems, and a final temperature. So we can sort of see that data. But in part A, it wants to know which is the limiting reagent for this particular experiment. And so what we want to do is, I'm going to jump to the next slide, get rid of that part B part, we'll come back to that, is how do we figure out who's the limiting reagent in all 4 trials. And we can see in all 4 trials, oh, the volume of hydrochloric acid is the same in every case, but the mass of magnesium oxide added is different, or at least there's pairs, 2 pairs where 0.25 grams have been added and 2 pairs where half a gram is added. So who is the limiting reagent? So what we would want to do is, we've got the chemical reaction up there, is we need to consider what the moles of each of the samples are. And on the AP exam, one of the places that we can get a point somewhere on the AP exam is showing how we calculate moles. because I know that we've got a volume of 100 milliliters of a 1 molar solution. And I think for many of us, we could sort of say, oh, well, I can do that in my head. If I've got 100 mils, which is 1/10 of a liter of 1 molar solution, I know that's 1/10 of a mole. But on the AP exam, we have got to show our work. So we're going to say 100 milliliters times 1 liter over 1,000 milliliters times 1 mole of HCl in 1 liter. And there, 0.100 moles of HCl. So there's our moles of HCl calculation. We've shown our work. This is not a complicated calculation by any means, but on the AP exam, moles are very important. Stoichiometry is very important. And so we've got to show that work. And in the second case, we say we've got 0.25 grams of magnesium oxide. And remember that 1 mole of magnesium oxide contains, let's see, the molar mass of magnesium is about 24.3 and 16 for the molar mass of oxygen. So 16 and 24.3, that sounds like about 40.3 grams. And so if we've got our calculator, we can probably come up with 0.0062 moles of magnesium oxide as our initial amount. So check it out. We have 2 different ways to calculate moles in this particular case. And so we've got to show both of those calculations, because more than likely on the AP exam, those calculations are going to be worth a point. Since they're 2 different, it's conceivable they could be worth 2 points. So, but we haven't figured out who the limiting reagent is. But we can check it out up here. If we look at this reaction, if we've got 0.1 moles, oops, I'm sorry, that's the 0.1 moles is the hydrochloric acid, and the 0.0062 moles for the magnesium oxide. We can see pretty easily that 0.0062 moles, if we compared to the hydrochloric acid, we need twice as much hydrochloric acid. So 2 times 0.0062 is 0.0124. So we've got more than enough hydrochloric acid to react with the magnesium oxide. So we can establish that if we just say let's see, where is my pin? Because I want to double check that I've got my, yep, there it is. And so let me go back real quick. I'm going to sort of get rid of that and get back. So now we're going to say that the 0.0062 moles of magnesium oxide requires 2 moles of HCl for every mole of magnesium oxide. And so that's 0.0124 moles of HCl. And so that's clearly we have excess. And so we've established that limiting reagent for the part A, that's going to be magnesium oxide is our limiting reagent. So if we go now to the next part, in part B, we are told that one of the trials is inconsistent with the data on the other 3 trials. Identify the trial with inconsistent data and draw a line through that data from that trial in the table above. So we've got to pick one of those 4 trials has data that's inconsistent with the other 3. And so what I'd like you to do is to take a moment and see if you can figure out, is it trial 1, trial 2, trial 3, or trial 4 that has inconsistent data? So that's sort of a 4-headed coin. You have to pick one of them. But the most important part is going to be, can you explain how you identified the inconsistent data? So let's look, take a moment and let's see if you can figure out which is the inconsistent data. So Mr. Akampura has got the poll up. So we're not going to be able to sort of do the explanation part, but we can certainly do the choice part, the 4-headed coin part. Which of these has that inconsistent data? And this is a challenging question because of that table and all the different numbers that are there. So we'll give you a few more seconds to sort of contemplate which of those trials is going to be the one with the inconsistent data. And it looks like it's sort of between trials 1, 3, and 4, we have the most number of choices. So,
and we've got a lot of reading to do here, so we'll give it about 30 more seconds.
Sure. And I know that one of the, what sometimes will throw students off are those different initial and final temperatures, that they can be sort of some of the places that the students go to sort of try to figure this out.
So possibly the first calculation would be to get the temperature change from the initial and final values.
Right.
Okay, because I'm going to end up polling here at 2 minutes.
All right. So what we can see in the table, if we look at the volume of HCl and the mass of the magnesium oxide added, in the case of the volume of the HCl, everybody gets 100 mils. But we can sort of check out, oh, there's 2 25.25 gram samples and 2 0.5 gram samples. So it looks like in this experiment that we're doubling the amount of magnesium oxide. It's the limiting reagent, so the hydrochloric acid is in excess, so we don't really worry about the hydrochloric acid. But then if we look at that, just like Mr. Akampura suggested, and we had been talking about mass and specific heat and change in temperature, let's look at the delta T for these 2 experiments. In trial 1, we see it's 1.1 degrees Celsius. In trial 2, it's 4 degrees Celsius, 4.1 degrees Celsius. In trial 3, it's 2.1 degrees Celsius. And in trial 4, it's 4.0 degrees Celsius. And this is sort of experimental data using thermometers or maybe a digital thermometer. So we're not going to expect like really nice, clean numbers. But check it out. In those 2 cases where we had added 0.5 gram of the magnesium oxide, those delta T's are essentially the same at 4 degrees. But with the 0.25 grams, which was half the amount of magnesium oxide, we've got one experiment, trial 3, which has a half the delta T change, and trial 1, which is 1/4. So when we think about which trial is inconsistent, yes, we're thinking that it's going to be trial 1. Is going to be the inconsistent trial because that temperature change is out of line with the other three experiments. So, so what we want to do is then go on and draw that line through that trial 1. Because by drawing that line through it, we'll be less likely to be thinking about that particular trial in subsequent questions. So I already have a line sort of through that trial in the next question, part of the question. So in part C and D, it asks us to use the data from one of the other 3 trials, not from the trial you identified in part B. Assume the calorimeter has a negligible heat capacity and that the specific heat of the contents of the calorimeter, that is the solution, is 4.18 joules per gram degrees Celsius. And that sounds pretty much like the specific heat of water. And we're to assume the density of the HCl is 1 gram per milliliter. So in part C, we're being asked to calculate Q. So I'm going to go to the next slide where we just have that part C part, and we're supposed to calculate the magnitude of Q, the thermal energy, when magnesium oxide is added to that 1 molar hydrochloric acid solution. And so I've already sort of set this up. So let's sort of substitute in the quantities because we have to be careful. We got a negative sign. And so now we need the mass of the solution. Well, the mass of the solution if we say, well, let's look at trial number 2 for doing this calculation. The mass of the solution is 100 grams. We were told the density of HCl is 1 gram per milliliter. So 100 mils is 100 grams and half a gram of the magnesium oxide. And so it's important because at the reading, when we grade the exams, while half a gram is not going to change the magnitude of the heat transferred, it is going to make the difference between whether a student could or could not get a point for this calculation of the magnitude, because we have to include the mass of the solution. So both the HCl and the magnesium oxide. And so we've got our specific heat, 1.8 joules per gram degrees Celsius, times that delta T, which we had calculated to be 4.1 degrees Celsius. So, so when we look at that calculation, we're going to come up with a number that's negative 1.72. Let's see, 1.72 times 10 to the 3rd joules. So for the total amount of heat transferred. Now, we're asked to calculate the magnitude. So at the AP reading, we're not going to pay attention to the sign of that number, the 1.72 times 10 to the 3rd joules. We are, in this case, because it's only asking for magnitude, we don't have to have the sign. So whether it's a positive or a negative doesn't make any difference in this part, but it does make all the difference in the next part of the calculation. So I'm going to jump forward because in part D, and then right here, I'm going to say this was minus 1.72 times 10 to the 3rd joules, that in this next part of the experiment, we're asked to determine the student's experimental value of delta H for the reaction between magnesium oxide and HCl in units of kilojoules per mole of reaction. Well, in this particular case, delta H is in kilojoules per mole. Well, delta H is just the Q of the reaction over the moles of the limiting reagent. And we know our limiting reagent is magnesium oxide. So we can calculate this delta H from the Q of the reaction, which we just had calculated in part C, which is the minus 1.72 times 10 to the third joules, over the moles of the magnesium oxide in trial 2 that reacted, and that was 0.5 grams. We had calculated in the previous case that the moles was, let's see, the moles would be I think it was 0.0062 or something like that. But in this case, we've got twice the mass. And so this is going to be 0.0124 moles of magnesium oxide. And so when we do that calculation, we're going to get a value of negative 1.39 times 10 to the fifth joules per mole of magnesium oxide. But the question was wanting to know the kilojoules per mole reaction. Well, the kilojoules is pretty easy to deal with. This is going to be minus 1.39 times 10 to the second kilojoules, because we know that there's 1,000 joules for every 1 kilojoules. So we've got 10 to the fifth, so we're going to divide by 10 to the third joules to get to kilojoules. But the conversion from moles of magnesium oxide to moles of reaction is a little complicated, but let's look at it this way. This is moles of magnesium oxide. We'll just do a conversion. And if we look at the reaction here, we can see 1 mole of magnesium oxide, because that's the coefficient, in the reaction in 1 mole of the reaction. So that's a 1-to-1 stoichiometry. So that's going to end up with minus 1.39 times 10 to the second kilojoules per mole of reaction for the delta H for this reaction. Remember, if we had just used Q is equal to mass times specific heat times delta T, this is an exothermic reaction, delta T would have been positive. Students who just use Q equals MC delta T, they might have lost the negative sign unless they remembered, oh, this is an exothermic reaction because the final temperature is higher than the initial temperature. That means delta H is negative. We don't,
John?
Yes.
We have a couple of questions from our studio audience. One question is that in the MCAT equation, how do you get the mass value? And I think it's important to emphasize that it's the mass of the solution, not the mass of the reactant. So
right. We can see in the equation here that the mass, the specific heat, and the delta T are all for the solution. Because that's what's hot. It's not just the magnesium oxide that's warming up. And this is a very common mistake that students make. Another question was, if perhaps a student had chosen one of the other trials as the inconsistent one and then did their calculations based on that, how would their answers be scored? As long as there was no math error, the student who had incorrectly picked the inconsistent trial and used one of the other experiments, they would get all the credit.
Thank you.
As long as there was no math error.
No one would make a math error here. This is Kentucky, not Oklahoma.
Yeah. Right, exactly. So this was actually a delightful sort of problem that challenged many students, and the kinds of concerns, oh, the mass of the solution, that I had to add the mass of the magnesium oxide with the mass of the hydrochloric acid was a very common mistake on the exam, and the loss of the sign was also. All right, so we're getting down to about 15 minutes, so let's look at another problem. I'm going to sort of jump forward because another part of this problem is another common calorimetry thermochemistry kind of experiment problem that we see on the AP exam. And here we're being asked to determine an accepted value for the delta H for this reaction. Only now, instead of given experimental data like mass and delta T's, we're given delta H's of formation for all of these, for all of the reactants and products. And so this is a very common kind of, I think, a pretty straightforward kind of problem. And so what we're going to do is we're going to jump to the equation page, and just quick reminder, there's our Q equals mass times specific heat times delta T form. But then right next to it is the delta H of a reaction, is the summation of the delta H of formation of products minus the summation of the delta H of formation of the reactants. You'll notice also that there are some other equations in this section on thermodynamics and electrochemistry. And in this year's exam, it is only these two equations that you will be concerned with as possible mathematical relationships that you might need to use to answer parts of the two questions that are going to appear on the AP chemistry exam for this year, since units 8 and 9 are not being covered. So this second one is the one that we want to consider using for this particular problem. And it's really pretty straightforward. We're just going to sum the delta H's of formation of the products, magnesium 2+ and water, and subtract from those sums the sum of the delta H of formations of the reactants. And you'll notice something interesting. One of those reactants has a delta H of formation equal to 0. So really, this problem is just going to turn out to be that we're going to take magnesium Mg2+, which has a minus 467 kilojoules per mole, and add to it the delta H of formation for water, which is a minus 286 kilojoules per mole, and subtract from that the delta H's of formation of the reactants, and that's going to be a minus 602 kilojoules per mole plus 2 times 0 kilojoules per mole, the delta H of formation for H+. Notice the 2. I'm multiplying each of the other 3 delta H's of formation by the coefficients, or actually it's a quotient of the moles of that reactant or product over 1 mole of reaction. And so we can see pretty quickly that when we do all those numbers, that we're going to come out to, let's see, 467 and 286. And then, but one of the things we got to watch out for is all these negative signs. So we're going to get this minus, what is that going to come out to be? About minus 753 for the reactants, minus 753 kilojoules per mole. And then a minus, which is a plus, 602. And so that's going to come out to be about a minus 151 kilojoules per mole for the delta H as calculated from the delta H of formations. And this is a common kind of problem, and it can get twisted around a little bit where, oh, what happens if we give you a delta H of reaction and ask you to calculate a delta H of formation for one of the reactants or one of the products. So that's another game that could be played. So, okay. And Lou, you can interrupt if any questions appear from
I am keeping an eye on the chat box, John, and I will just say that I don't think many textbooks do this, but I will actually, when I'm teaching, just differentiate between the experimental delta H of reaction, which is what you would get from calorimetry and using the equation that Q equals MC delta T and delta H equals Q over moles, and the theoretical delta H of reaction, which is what you might calculate from the delta H of formations. And then you can certainly see questions where you might ask for a source of experimental error and why those two might differ.
Yeah.
And we put these questions on the AP Chem exam to really see, are you doing these experiments and are you following them?
Right, because in fact, we had the experimental value of 139 kilojoules per mole rather than the minus 151. So our experimental value was a little more positive than the theoretical value. So not as much heat was measured as being transferred in that reaction. And we could understand that in terms of that calorimeter, which we were told we didn't have to worry about, but in fact is a source of, it's going to absorb some heat. And that's proven in this particular comparison. That was actually another question, another part of the question on this question that I did not include on.
And we had one more thing. We had a student ask where the value of negative 753, where that came from. And I think that, well, I'll let you take that.
Okay, that was just the sum of the delta H of formation of the products. So 467 and 286. And I apologize, I sort of did that in my head. I think I did it right. So that's the 753. So that was just the sum of the product delta H's. And then this was minus the minus 602. So that's how I came up with the 151. Okay. So we've got about, correct me, Lou, about 8 minutes.
About that.
And so this next problem is actually very similar to the one that we had just done, in that we have another reaction as we did before. We have a data table which tells us the concentration and volumes for each of the three reactants. And in this particular case, here again, a student performs an experiment to determine the value of the enthalpy change, delta H of a reaction. For, in this case, this is an oxidation reduction reaction. The one we were looking at before was just the neutralization type reaction. And, and so this problem is identical to the problem we just did, but the reaction is totally different. The initial information that we're given is very different, but we're still going to end up trying to calculate a delta H reaction. We're not going to have time to do all of that problem in this particular case, but I did want to sort of show you the similarity, and this was a 2018 AP Chemistry exam question, where again, use the balanced equation and the information in the table, determine the reactant is limiting reagent. Justify your answer. So again, we had to do a limiting reagent kind of calculation, and I don't think we're gonna do it, we have to have the delta T. Now, remember in the previous case, we had initial and final temperatures that were given to the student. In this particular case, the student has to interpret a graph to come up with that delta T. And so we can see that there's that initial temperature at about 20 degrees Celsius. And then there's a final temperature up here at about 32.5. So again, this is an exothermic reaction. Final temperature is greater than the initial temperature, but the students had to come up with what was the temperature change. So here is another kind of problem like that. And then again, we're back to using Q of reaction as Q of the solution times the mass times the specific heat times the delta T of solution. And in this particular case, check it out. I'm jumping back now. Check it out. We had 5 milliliters of each of those 3 reactants with 0.5 molar. And so we would have had 15 milliliters of solution, and we would have had to determine the mass of that 15 milliliters. And since those were very dilute solutions, it really didn't give us any information about density, because we know for very dilute solutions that essentially the density of the solution is the density of water. So this was a more interesting but very similar kind of problem. One aspect of this that we might just take a real quick moment to consider is the net ionic equation for this reaction, because this question, this net ionic equation, really challenged a lot of students. And I think the challenge might have been, and some of you can go ahead and maybe type into the chat what you think the challenge might have been for some of the students to come up with a net ionic equation. But it's pretty interesting. Look at every one of these compounds, with the exception of water. They all are sodium salts. And what's scary about all of these sodium salts is a number of them are kind of unfamiliar to us, but shouldn't really get in our way to come up with an ionic compound, because we could certainly start over here with a product with the sodium chloride, because we know sodium chloride is soluble, because all sodium salts are soluble. And so we know that that product is just going to be Cl minus and H2O, that part. And we could use the same approach with the sodium sulfate. Again, the sodium ions drop out, and it's the sulfate ions that we've got to worry about. But I better put my coefficients in there, because if I was a student who was writing that and left out my coefficients, the readers would leave off the points. The real trickier ones are over here, but sodium salts, and we'll just leave the S2O3 in, and the OCl minus with a 4, and then the 2 hydroxides, because all of these were sodium salts. So that's what turned out to be that net ionic equation. So I think that we're getting pretty close to the end of the time today. And I was going to maybe move this a little bit. Oh, I guess I can't. I was maybe want to show one more thing. So Lou, were there any other questions from the students that they might need addressed?
John, I think we answered all the questions, and they can always ask their teachers or send emails to me. And again, this will be available on the KY AP 2020 website, probably by tomorrow, along with a PowerPoint and notes. So thank you so much.
Okay, well, thank you. It was a lot of fun, and I hope that students have seen some of the very common cases. There was one other problem that was included in the PowerPoint that we didn't get to, which is bond energies. And so I want to reiterate that that is another question that's very common on the AP exam, and that but we just did not get to it today.
And that's fine. Thank you so much. Everyone stay
Okay.
healthy out there, and I hope to see you again in person maybe. Take care. Bye-bye.
Okay, bye-bye, Mr. Akampura.